again, AP Calculus student, Mr. Record here. We're still in section 7.1 of Larson's 9th edition. We're talking about the area that lies between two curves. And in our example 4, we have something very special planned for you. Curves that intersect at more than 2 points. Now on the surface, that may not seem like a big deal, but is it ever a big deal? And I think in this particular example, if we could rely on the sketch, I think it's going to tell us everything that we need to know. Now the problem with this, it's not the easiest sketch in the world. You've got a cubic here. Maybe you know a little bit about those graphs, look like, you know, an S shape. But I would say that if you don't have the ability to use the calculator on this question, is just do as I've done before in my other videos and just rely on a nice little t-chart. So for the t-chart that we're talking about, I'm just going to let x be 0 to start with, and it's pretty clear that if I graph f of x here, if I graph f of x here in blue, that I would have a 0 value. No problems there. And then maybe if we let x be 1, let's see, f of 1, I would have 3 minus 1 minus 10, which is 3 minus 11, or negative 8, right here. So 1, negative 8. Pay attention to the scale change here. I have my increments along the y-axis in groups of 2. F of 2, let's see, what's f of 2 going to give me? 3 times, 2 cubed, 3 times 8, pretty large to start with, 24, but that's going to change when I subtract a 2 squared or a 4, and even more so when I subtract a 10 times 2 or a 20. In fact, that's just 0, isn't it? And then let's see if we can fit f of 3 in. F of 3 would be 3 times 3 cubed, 3 times 3 cubed, 3 times 27, 81. Then I'm going to subtract 3 squared, which is 9. And then I'll subtract 3 times 10. Oh, can I just barely squeeze that? Maybe. 81 minus 30, no, 81 minus 39, that's not good, is it? That's a pretty large number that's off my grid here. But I do know that it's going to be way up there at least. So I don't think we're going to probably get any other desirable values if we let x be 4. So let's move to the other side. Let's finagle f being, say, an x value of negative 1. 3 times negative 1 cubed is negative 3. Negative times negative 1 squared. Now, double check that. That would be negative 1, right? Negative times negative 1 squared, negative positive 1, negative 1. And then 10 times negative 1 would be positive 10. So we've got negative 4 plus 10, or a 6 for the y value. All right, things are coming together. Let's try f of 2, negative 2. 3 times negative 2 cubed would be 3 times negative 8, or negative 24. Looks a little bleak now, but I think that's going to change. Subtract negative 2 squared, which is another minus 4. It's just getting worse and worse, but we'll rebound very quickly when we plug negative 2 in for the negative 10x with a positive 20. Negative 28 plus 20 is negative 8. Now, here in a little bit, I am going to break out the TI Inspire calculator to do some calculus on this. So it seems kind of silly that, we could have graphed it with the calculator, but I wanted to make sure that everyone was very comfortable with the fact that T-charts will work. They are very time consuming, but they do get the job done. Now, if you connect these points, it seems a little kind of erratic, the behavior here. But if you think about, what the typical cubic is going to look like, you would come up with a sketch that might indeed look something like this. Now let's keep in mind, this is just a sketch. It is nothing more than that. I'm not going to say that the maximum and the minimums do actually occur at these two high points and low points. That may or may not be the case. But for the purpose of this problem, we're just going to use the sketch to help us identify the region that we're finding the area of and the boundaries. Okay, now your reward for sketching that F is now to sketch the G and do the same thing all over again. And I'll use green for this. Luckily, this is a quadratic. It won't take nearly as much time. When x is 0, obviously you have a value of 0. When x is 1, we have negative 1 minus 2. I'm sorry, let's take that back. Negative 1 plus 2. Negative 1 plus 2 is 1, right? Now, careful, look at where I'm placing that point, 1, 1. We have a scale change on our y-axis that we have to consider. Okay, maybe I'll have to write out some of these next ones. G of 2 would be negative 4 plus 4. Well, that's just going to be 0. How about G of 3? G of 3 would be negative 9 plus 6, which would be negative 3, which would be right about there. And then I think if we tried to find G of 4, we might find that we're going to be off our scale. Negative 16 plus 8. Oh, no, I'm still okay. Negative 8. But that's about all I have room for horizontally. So far you can see that I've got this much of the sketch. Now, if you know a little bit about the symmetry of your parabola, you can probably rest assured that the sketch is going to have the same mirror image effect on the other side. But you could also verify that very briefly by figuring out values for negative 1 and negative 2. And I'm going to leave that for you guys to do on your own, but you would end up with the following values. Negative 1 for x has a y value of negative 3. And looky here, negative 2. Negative 2 for your value of x has a value for y of negative 8. That couldn't have worked out any better because it also forms a very important point of intersection. So now let's go ahead and shade in the regions that we're talking about. In fact, we have two. We have this guy over here that I will shade in yellow. And let's just shake things up a little bit. Let's shade this guy in this wonderful pea soup green color. So we have the area of a yellow region and the area of a green region. You want to take a guess, how many integral expressions is it going to take to find this area? And my class says 2, and they are right. Good. You've got the yellow region here, which I can also label as region 1, has a completely different top function than bottom function. And it has different boundaries for that matter. So we will, for that area of region 1, say we will integrate from boundaries negative 2 to 0. Negative 2 to 0. And we would take the upper function, which would be identified here with my blue graph or cubic graph. So that would be 3x cubed minus x squared minus 10x. And then I would subtract my quadratic, the quantity of the quadratic, negative x squared plus 2x. And then I would do all this integration with respect to x. And that's only going to give me half of my answer. Well, then to find the area of the other region, all right, a region in green or labeled by the number 2, I would have slightly different boundaries. Can you guys see what the boundaries would be here? 0 to 2. And the top curve is now going to be the quadratic function, the negative x squared plus 2x. And then I would subtract the cubic. All with respect to x. And it's pretty clear in this problem that if I can find A1 and A2, all I would have to do is add them together. Make sense? Now, I'm going to spare the details of this integration because, quite frankly, this is a very easy integration problem. If you're already at this point in AP Calculus AB, you're probably nearing the end, getting very close to the AP exam itself, and you've gone through several kinds of integrations, U substitutions and other various formulas. I don't think integrating simple polynomials is going to be a problem. So now let's rely on a little bit of technology in order to answer this. And maybe I can even show those of you who are TI Inspire users a shorter way to enter these into your calculator. So we'll get the Inspire software up here and running, and you just need to go to a blank scratch pad. And I can get rid of this here. What we're going to do is define the functions. Okay, to define a function, it's very simple. You can just choose some name that you want to call it. And to make things easier, we could just use the names that were given to us in this problem, like f of x. So you would just type f parenthesis x. Nothing really happens yet. But to define a function, you're going to use um, the secondary feature of the math template, which to get to that, you would hit Control. You can see how Control lit up in red, and then the template button, and then basically what you see is a colon and an equals. Colon and then equals. That means you're about to define the f of x. And this f of x was the cubic. Is that correct? The cubic? And I might have to ask my class here because my memory is very, very poor. The cubic was 3x cubed, was it not? And what happened next? 3x cubed minus x squared minus 10x. Okay, awesome. And when you hit enter, it's just going to say done. It's like, okay, well, did you do anything for me? Well, yes, it did. It's remembering that f of x. Okay, we just do the same exact thing with the g of x. G of x defined as, whoops, that's not good. Let's make sure that we get that defined as after that parenthesis. Defined as, and I believe this one was negative x squared plus 2x. And we got him defined, and he's good to go. Now all we have to do is enter f of x and g of x. And the reason why this was helpful is because we're going to have to do that twice, aren't we? Everybody understand that? So to get our first definite integral symbol, you recall perhaps there's a shortcut, shift plus, a great handy little shortcut to get a definite integral. We have negative 2 as our lower boundary and 0 as our upper boundary. And obviously I'm going to be finding the area of region 1 in this case. And then this is the cool part. All we need to do is just enter f of x minus g of x. And it's important. We do need to put the f and the g. Let me get my cursor out of the way here. We do need to enter the of x part. And it's kind of nice that the calculator does bold the f and the g. It's just saying to you, hey, I know what those guys are. I remember them. Hit enter, and then boom, the answer is 12. All right, now don't forget we have another calculation to do, second plus. This time the boundaries go from 0 to positive 2, I believe. But now we'll start with which function first? The g of x minus the f of x with respect to x. And this answer, ironically, is 12. Yeah, sometimes I wonder if this is the best example to show everyone because, oh, they're both 12. That's to be expected, right? Well, not necessarily. You know, if we go back to our document here, our Smart Notebook page, we find that these two regions, this yellow shape and this green shape, are definitely not congruent, right? They're not the same exact size and shape. Now, they may be the same size, but they're not the same shape. So it's just sort of an ironic twist, a coincidence, if you will, that both of those end up being, let's switch back to my black here, both of those happen to be 12. Well, there we have it. Add the two 12s together and you found the area between these two curves. Curves that might intersect at more than just the 2 points as the endpoints. Hope this helps, and I'll see you next time.